Okay, so what we're going to start with is we're going to start with the electron configurations for atoms of elements. For some reason, I am in a bad location on my iPad. With this, what we're going to be doing is we're going to develop the basic electron configuration. We are going to develop the noble gas electron configuration. We are going to develop the box diagram. And using the box diagram, we're going to come up with some of the quantum numbers. Then we're also going to be, as I mentioned, developing the electron configuration. For a set of anomalies. Now, when we get into this set of anomalies, we're only going to do a small section of them. There are anomalies scattered throughout the entire periodic table, but we're going to only do group 6 and group 11. And the reason I focus on group 6 and group 11 for these anomalies is because they're the only groups where every single atom in the group behaves as an anomaly. So that's why I focus on group 6 and 11. Again, there are anomalies scattered throughout the entire periodic table, primarily when you get into the larger atoms. But group 6 and group 11, every element in that group behaves the same way. And so that's why I focus on those particular anomalies. Now, there is one more thing I want to say before we move on, and that is when you look at Blackboard, you're going to see that we have a test scheduled for a week from Thursday. And on that test, you will be developing these electron configurations. And to make things easier with the electron configurations, the basic electron configuration, I do it for element 1 through 18. That is because once you get past element 18, it gets quite long, or can get quite long. And so I usually focus on the noble gas configurations for anything in element 19 on. And that is just so that you're not spending all of your time writing out this monstrous electron configuration. Now, today I am going to illustrate both the basic electron configuration and the noble gas configuration for some of these elements. But again, I wanted you to realize that when it came to test time, it'll be element 1 through 18 and element 19. Now, box diagram, again, the box diagram I ask you to develop will be for element 1 through 18. And then the quantum numbers, I will give you the box diagram. And ask you to identify specific ones. But that just gives you a little bit of what you can expect when it comes test time. Okay. I just realized I don't have a periodic table pulled up. So let me pull up one real fast. Okay, so let's get going. On Thursday of last week, we did carbon. Let's look at oxygen today to start out with. Oxygen is element number 8. So it's going to have 8 protons and 8 electrons in a neutral atom. When we develop an electron configuration, we always start at the top of the periodic table. And if you go back to the diagram I gave you on Tuesday of last week, you would see that's the 1s. And so it's 1s. And the maximum number of electrons allowed in that 1s is 2. Then we move on to the 2s. And the maximum number of electrons allowed in the 2s is 2. And then we move on to the 2p's. And we need, oxygen is the 4th element in the 2p's, so it would have a 4. Now, one thing I want you to note that I did not describe on Thursday is if you add the subscripts, I'm sorry, the superscripts. If you add the superscripts, that equals the number of electrons. So in this case, 2 plus 2 plus 4 is 8 electrons, which is what we were supposed to have. Any questions about that? Okay, with our noble gas configuration, basically a noble gas configuration is a shorthand notation. And when we write this shorthand notation, we identify the noble gas that preceded our element. In this case, the noble gas that preceded oxygen is helium. And we place that helium, or the symbol for helium, in brackets. When doing so, what you are saying is that you can ignore everything through helium. You do not have to write out any electron configuration prior to helium. You only need to write out what comes post helium. And if you look at what the next thing, if you're following along in that diagram I gave you on Tuesday of last week, the thing that came after helium was the 2s's. And the maximum number of electrons was 2. And then we have the two p's with the maximum number of electrons as 4. And so the noble gas configuration for oxygen is helium 2s2 2p4. Questions about that? Okay. Now what we're going to do is we're going to develop the box diagram. Now I'm going to develop the box diagram based off of the basic electron configuration. When we develop the box diagram, you are combining your knowledge of quantum numbers with your knowledge of electron configurations. When we talk about the S subshell, how many orbitals does the S subshell have? Anyone?
1.
It has 1. That is why you draw a single line or a single box and you label it as the 1s. Well, the same thing is true for the 2s because it is still an S subshell. So it's going to have 1 orbital. How many orbitals does the P subshell have? You can type it if you want, or state it. It has 3. That's why you put 3 lines to represent the 2p. Now we start placing our electrons. The first electron that goes into an orbital is going to go in spin up. That is just common notation, is that it goes spin up. The second electron in that orbital goes spin down. For the 2s, the first electron goes in spin up, the second electron in spin down. Now, when you get to the p, because there is more than 1 orbital in the p subshell, because there is more than 1 orbital in the p subshell, you place 1 electron in each orbital before pairing. So we're going to place 1 electron spin up in each orbital before we pair to get a total of 4. Any questions? Okay. Let's take each of these electrons in the p subshell and let's develop the quantum numbers for them. So for this, I'm gonna number them 1, 2, 3, and 4, just so that we know which ones we're coming up with. Now, before we can get into that, we're going to have to know we know the N value and we know the L value. because anytime we have a p subshell, it means that L is equal to 1. We know the M sub s, because if it's an up arrow, it's a plus 1/2. And if it's a down arrow, it's a negative 1/2. The only thing we really need to figure out is going to be our M sub L, which is going to be directly related to the lines that we have. Now, M sub L can be anything from a negative L to a plus L. So it can be, if L is equal to 1, that means it's a negative 1 to a plus 1. And so what we do is we number these lines in order of a number line. So on a number line, you would start with negative 1, then 0, then 1. Now we have all the pieces, and it's just a matter of writing it out. And it's always written out in the same order. It's always N, followed by L, followed by M sub L, followed by M sub S. So let's look at this first electron that we put into the orbital here, number 1. Its N value is going to be 2. Its L value, because it is a P subshell, is 1. Its M sub L is a negative 1. And its M sub S, because it's spin up, is a plus 1/2. The second electron we added, number 2, it's going to be an N of 2, because that's the principal quantum number. The L is still going to be equal to 1, because it is a P subshell. The M sub L is 0, and because it's spin up, it's a plus 1/2. Number 3, its N is 2, because it's in the second shell. Its L is 1, because it's a P subshell. Its M sub L in this case is 1, and it's spin up, so it's plus 1/2. Then we put in number 4. Number 4 is going to be 2, because it's second shell, 1, because it is an L subshell, a P subshell, a negative 1, because it's in the first orbital, and in this case, it's a negative 1/2 because it was spin down. Questions? I was asked, so we have to write the quantum numbers for all electrons in the last subshell? Not necessarily. On an exam, I will give you the box diagram, and I will highlight at least 3 electrons that you have to give me, but they won't necessarily be just in the last subshell. It's just going to be a matter of which ones I ask you for. I was asked, how do we know plus 1/2 minus 1/2? That is related to your spin. If it's an up arrow, well, come on. No, I'm having issues here. If it's an up arrow, it's a plus 1/2. If it's a down arrow, it's a negative 1/2. So it all depended upon which direction the arrow was facing. Other questions? Okay, one question I had is for whatever electron we're given, will the n value be based on what orbital that electron is in, or the orbital of the element itself? The n value is always going to be based off of the shell, which came from your electron configuration. The next question I was asked was, how do you know which way the spin goes? It is a common notation to put spin up first. So the up arrow will always go first. And then it'll be followed with the down arrow. Did that answer everybody's question? Do we only do the box diagram for P? Oh wait, I skipped one. How do I know 2P only has 3 lines? What it boils, so the reason we know P has 3 lines is because the P subshell is L equals 1. That means our M sub L is anything from a negative L to a plus L. So it's a negative 1 to a plus 1. So if we go on a number line, that means it's got 3 lines, because you will have a line for each of those numbers. And how do we know, do we only do the box? No, well, I did the box diagram for oxygen. I didn't do it just for the P. I did it for oxygen. I just only decided to do the quantum numbers for the P. I'll do another example and I'll mix it up just so that you'll see it's not always for the P. Other questions? Okay, let's look at another example. Let's do aluminum. Aluminum is atomic number 13. So it has 13 protons and 13 electrons. For the basic diagram, we have to write an electron configuration for all of them. Oh, let me go back and answer a question before I do that. And the question was, what is this 1, 2, 3, 4? It was just identifying which electron I was writing the quantum number for at any given time. So there was no meaning behind it other than it was identifying which quantum numbers I needed. Let's look at another example, and hopefully the more examples we can look at, the better our understanding. So for this one, basic, you start out at the top. So 1 and the S subshell, and the maximum number of electrons in an S is 2. Then we go to the 2 S subshell. The maximum number of electrons is 2. Then we go to the 2 P subshell. The maximum number of electrons is 6. So far, we have distributed 10 electrons. So we move to the third row on the periodic table. The next thing we encounter is the 3s, and there are 2 electrons. And then we encounter the 3p, and aluminum is the first element in the p's. And if you add up the superscripts, I could spell. That equals 13. Just like your number of electrons. Now for the noble gas configuration. With the noble gas configuration, we identify the noble gas that preceded aluminum. And the noble gas that came before aluminum is neon. You place the neon in brackets. Now basically what we have just said is we have everything that neon has, meaning you do not have to write out anything that neon has. We have everything neon has. All we need to include is what aluminum has that neon does not have. Aluminum has the 3s, 2, and the 3p, 1 that neon does not have. Now for our box diagram. The S subshell, according to quantum numbers, has 1 orbital. So it has 1 line. That is going to be true for any S subshell. It'll have only 1 line because it has only 1 orbital. The P subshell will have 3 lines because it has 3 orbitals. The S subshell has only 1 line because it has only 1 orbital. The P subshell has 3 lines because it has 3 orbitals. Filling in this box diagram, according to our basic electron configuration, the 1s has 2 electrons, so it's going to be 1 spin up and 1 spin down. The 2s has 2 electrons. It's going to have 1 spin up and 1 spin down. The 2p has 6 electrons. Because there is more than one orbital, you place 1 electron in each orbital before pairing them up. The 3s has 2 electrons, 1 in spin up, 1 in spin down, because it only had 1 orbital. And the 3p, aluminum was the first element in the 3p, and so it's got only 1 electron in the 3p, and it goes in spin up. Now this time I'm only going to do 3 sets of quantum numbers, and I'm just going to pick 3. We will do we'll do this one. And this one. And this one. Those are going to be the 3 electrons we're going to get the quantum numbers for. Okay. Before you can get the quantum, you've got the N. Technically, you have the L. You need the M sub L before you can do anything more. So this comes back down to if we have a P subshell, L is equal to 1. Therefore, our M sub L is going to be anything between -1 to a +1. So it's going to be on a number line. It's going to be -1, 0, and 1. So we can go in and put those numbers in for our P's. For an S subshell, L equals 0. So M sub L is going to be anything from a -0 to a +0, or in other words, it's simply equal to 0. So you can put a 0 in for any S. And that gives you your M sub L values. Now, let's get our quantum numbers. For the first one, which is going to be the one that was in red, the 2 tells me my N value. The letter tells me my L value, and the arrow tells me my M sub S value. We always write them in the same order with N first, so that would be a 2, followed by the L, which is a 1, followed by the M sub L. Because we assigned this one a 0, that means that M sub L is 0. And then the M sub S, because it is a down arrow, is a -1/2. For our blue arrow, your N is represented by the number, your L is represented by the letter, your M sub S is represented by the arrow, and your M sub L is represented by the number you assigned for the orbital. So this one would be a 3, 0, 0 plus 1/2. Finally, for the green arrow, again, the number represents N, the letter represents L, the arrow represents M sub S, and your M sub L was represented by the orbital note that you assigned it. So the numbers for the third one would be 3, 1, -1/2, I'm sorry, -1, +1/2. Questions? Let's do one more before we do an anomaly. And let's do iron. Oh, wait, no, excuse me. Okay, so I did have a question. This is around the noble gas configuration. Could you explain why neon doesn't have the 1s, 2s, etc.? Okay, so let me work on that one down. Let me show you down here. So we were working with aluminum, and we said it was 1s2, 2s2, 2p6, 3s2, 3p1. If I do neon, if I were to write the noble gas, the configuration for neon, neons is 1s2, 2s2, 2p6. So basically what you did when you made the noble gas configuration is you went and said, okay, I have the aluminum has everything that neon has. So it winds up being, so when we do aluminum with the noble gas configuration, we're saying it has everything neon has. All we have to do is explain what neon doesn't have, and that would be the 3s2, 3p1. Did that answer your question, Megan?
Yes, thank you.
No worries. Okay, like I said, I want to do iron because I want us to see that how complicated they can get. Iron is element, and I mean, this is only element 26 on the periodic table even. So that means its atomic number is 26. It means that it has 26 protons and 26 electrons. So we've got to put 26 electrons into the basic diagram. And we start at the very top of that diagram I gave you on Tuesday. And I think I rewrote it on Thursday, but I can't remember, with the 1s's. And it's 2 elements across. Then we move to the 2s on the periodic table, and that's got 2 elements across. Then we move to the 2p, and there are 6 elements across. Now we're down to the 3rd row on the periodic table, and that's 2 elements across. And then we're moving all the way across on that 3rd row. So the next thing we encounter is our 3p's, and that is 6 elements across. And then we move to the 4th row on the periodic table. And the first thing we encounter is the 4s, and that is 2 electrons across, or 2 atoms across. Then this is where we move into that n-1 or x-1 area. So this is the 3Ds that come next. The 3Ds come after the 4s's because the 3D is just slightly higher in energy than the 4s. And iron is the 6th element in the 3D. Now we develop it. You can see, I mean, I've only gotten up to the 1st row of transition metals, and already you can see how this basic electron configuration can become quite extensive. And so it's really nice to have that noble gas configuration at this point, that shorthand notation at this point, because it makes writing out the electron configuration so much easier, so much faster. So with our noble gas configuration, we're going to find the noble gas that came before iron. And the noble gas that came before iron is argon. Basically, by putting that symbol of argon in brackets, you can exclude everything through the 3p's. Because if you were to write out the electron configuration for argon, you would see that it goes through 3p6. So basically, you look at what happens on that 4th row. You can ignore everything from row 3 up. You just need to look at what happened on the 4th row. And what happened on that 4th row was the 4s2 3d6. Now at this point, I usually take the noble gas configuration to develop my box diagram, because it gets, you could see where the box diagram would become quite complex. Again, when it comes down to the box diagram, as far as me making you write a box diagram, I will only go up through element 18. Now, where it comes into quantum numbers, I may go past that, but I will give you the box diagram for the quantum numbers I want. That way I'm not making you write an electron configuration and potentially get it. If you got it wrong, I don't want you to get the quantum numbers wrong. So since they rely on each other. So again, I'm going to do the box diagram for the noble gas. So it's going to be my argon in brackets. Now, this comes back down to knowing how many orbitals. And if we look at an S subshell, Again, an S subshell means L is equal to 0. Therefore, M sub L is anything from a -0 to a +0, or in other words, it's 0. And it means it has only one orbital. A D subshell, D means that L is equal to 2. So M sub L can be anything from a -2 to a +2. And if you were to write that out on a number line, that's a -2, a -1, a 0, a 1, and a 2. That means that D has 5 orbitals. So the 4s has 1 orbital because it's an S. The 3D has 5 orbitals because it's a D. Now in the 4s, there are 2 electrons, one spin up, spin down, one spin down. In the D is treated just like the P's were because there is more than one orbital. You're going to place an electron in each orbital, spin up before pairing. So we're going to place an electron in each orbital, spin up before we pair to give us our 6 electrons. Let's see. We will deal with this electron. This electron. And this electron for our quantum numbers. Okay. So the first thing is we've got our N, our L, our M sub S. You just need your M sub L value. Again, when you're looking at a S subshell, there is only one option, and that is for it to be equal to 0. That's its only option. But for a D, that option is that it's a -2 to a +2. So you just number them: -2, -1, 0, 1, 2. And you will have your D. Your M sub L values for your D subshell. So for this red arrow, the N is 4. The L, because it is an S, is 0. The M sub L we determined had to be 0. And because I asked you for the spin up, that's a +1/2. For the blue arrow, the N value is 3. The L value is determined by the letter. It is spin up, so it's M sub S. And our M sub L we determined was a -2 because that is where it aligned. So this would be 3, 2, -2, and because I asked you for the up arrow, it's +1/2. Finally, for our green arrow, the N is going to be 3. The L is still a D. The M sub S is going to be spin up, and we determined that this one was 0 for the M sub L. So for the third one, it is 3, 2, 0 plus 1/2. Questions? Okay. Now what I'm going to do is I'm going to talk about the anomalies. Again, the anomalies are group 6 and 11. These exist because of 2 reasons. The first reason is that there is only a slight difference in the energy of the S subshell and the D subshell. Basically, what I mean by this is if I were to look, for example, let me actually do a couple of them. If I were to do 4S and compare it to the 3D with respect to the energy, you would see that there's only a very slight difference between those 2 lines. The same thing is true if I get into the 5S, Luna Bear is wanting attention, and the 4D. There is only a very slight difference. So anomalies exist because between the S and the Ds, there are only slight differences in energies. The second reason that they exist is because a half-filled half-filled or a half-filled full set of subshells provides an increased stability. So let me illustrate what I mean. And again, this is going to be true for all of them. It's not just true for the 4S3D, but I am going to illustrate it for the 4S3D in the time we have left. Let's take chromium, for example. Our typical way to fill has been that chromium would have been argon, and then we would have put in 2 4S's and 4 3Ds. But here is where the anomaly comes into play. Because we can take one of these electrons in the 4S and it can be promoted into the 3D. And when you do so, you get a half-filled 4S and a half-filled 3D subshell. We can do this because, again, the energy difference between the 4S and the 3D is very, very small. And by doing so, we have provided the element an additional stability because of the half-filled set of subshells. The same thing will occur with molybdenum. Molybdenum, you'll promote 1 out of the 5S into the 4D to get that half-filled, half-filled. So again, every single element in group 6 is going to behave this way, where one of the S's is going to get promoted into the D in order to get a half-filled, half-filled. Again, every element in group 6 is going to behave this way, where one of the S's is going to get promoted into the D in order to get that stability from a half-filled set of subshells. Now let's look at copper. Which is in group 11. If we typically fill copper we would have given it as argon. Four S2, 3D9. But again, the difference between the S and the D is the energy between those is extremely small. So one of those electrons in the S can be promoted up to the D. And when you do so, you get the anomaly filling. Where you have a 4S that is half filled and a completely full 3D. So you have just added some stability. Due to a half-filled full set of subshells. I'll answer your question in just a moment. So, by the way, anything that's not half filled or full is considered to be a partial. 9 is a partial. 8 is a partial. Basically, it's either half filled or it's full or it's considered a partial. So again, group 11 will promote an electron from the S to the D in order to get that half filled and full subshell instead of a full and a partial. This is true for silver. Silver will promote, one electron will get promoted from the S into the D in order to make sure silver has a full and a half filled and a full subshell. Now, in answer to the question, the first question that was in here, do we change the spin direction when added? It really is dependent upon whether or, so we did have to change the spin direction on the group 6. Because the first electron in any subshell, the first electron in any orbital, goes in spin up. So in group 6, yes, we did change the spin in order to make it go, in order to fill the orbital correctly. But you will notice in group 11, we did not change the spin. That's because of what was needed in order to achieve the full. The next question I was asked is, why is the half fill better than a partial? This comes down to the fact that let me take group 6 first to answer that question. With first of all, anytime you pair up an electron, meaning you have a spin up and a spin down electron, you have just increased the energy of the system. So in group 6, for example, we were able to take a set of electrons in the 4s that were paired, meaning slightly higher in energy, And we were able to disperse it so that you had two half fills, which they were all spin up. So that caused it to be slightly lower in energy, just because they were all spin up. Now, in answer to your question about why is a half full better than a partially full, it again comes down to energy. Even though we did not change the spin on the group 11, once you fill up a shell, there's a slight change in energy associated with filling up a shell. And so it's all about the energy, but again, these are, they're almost unrecognizable levels of energy, but they're there. And it's all about the energy. Is why we do the half full, why we say it's better than a partial, or a full is better than a partial, is because there's, yes, by pairing up every single spin, you are increasing the energy. But once you get a full shell, it's like it locks it down and makes it slightly lower. It's all about the energy. I will stay on and answer questions, but I also need to be respectful in case somebody else is having online class like I am. And so it is 10:40, and so I want to make sure that you have a chance to disappear if you want to disappear. Have a good day.
Dr. Yarborough, you said that you have office hours from 12 to 2 today.
Yes, I do.
Okay, and it's going to be through Zoom?
Yes.
All righty, I'll see you then.
Okay, sounds good.
Bye.
Yes, I know. I know. We're being a little testy. Being a little pissed. Yeah. That's why I don't like that sometimes. I was calling Luna Bear a pest, not